All right, here's 8.2 notes, page 1, sample proportions. So we're going to look at some of these normally distributed curves and some that aren't normally distributed. And we're going to look at an individual characteristic inside of that data. We can find the sample proportion, and sometimes we're going to refer to the sample proportion as p hat. It's p with that little accent mark on the top of it. And basically it's a basic probability. It's x, the number of terms that contain that characteristic, divided by n, the total number of terms in the population. Okay, suppose you conduct a survey of 1,000 U.S. adults and ask, who's the best president? Of the survey, 195 people said that Abraham Lincoln was the greatest president. And the rest of them said somebody different. So that means 805 said somebody else. So since there's only 2 answers that we're considering in this question, this is a sample of binomial distribution that we learned in section 6.2. It's either right or it's wrong. It's either a success or it's a failure. In this case, counting the successes is how many people responded that Abe Lincoln was the best president. So what's the sample proportion? The sample proportion is what our p hat is. We just take x, the number of successes, divided by the total number in this population. 195 people thought that Abe was the best president over the total in the survey, so 19.5%. Sample proportion. Make an inference as to the proportion of all U.S. adults. Well, we would consider if we could ask all U.S. adults which one their favorite president, we would assume that close to 19.5% of them would like Abe Lincoln. If this survey were repeated with a new sample of 1,000, we would assume that it would be close to 19.5. The sample proportion, or p hat, will vary from sample to sample, but it's going to be close. So it's a random variable with probability distribution, just like our binomial options were in section 6.2. Let's consider the binomial probability experiment here. There were 1,000 trials and the probability of success was 0.2. Using binomial probability, the probability histogram is given below. Can we assume that that thing is normal? By God, it looks normal. Perfectly bell-shaped curve. Now, I'm going to say this thing is perfect. What's the mean proportion on this thing? The mean proportion, if that is 0.2, the mean proportion would be, take the average and divide it by the total number of trials. Now, to test to see if we can assume that it's normal for these sampling distributions, we need to calculate the variance of the binomial distribution. The variance of a binomial distribution if you were looking at the guided notes, like, where did that come from? Well, that came from 6.2. The variance of a binomial distribution is this NP 1 minus P. And if that number is greater than 10, we can assume that the distribution is normal. So here's our second test for testing to see if the distribution is normal or not. In section 8.1, we needed to have more than 30 samples, okay? In this section, when we're sampling for these probability distributions, we need the variance of this binomial distribution to be greater than 10. Let's plug in our numbers. N, the number of trials, P, the probability, we used to call it probability of a success, and 1 minus P, we called that the probability of a failure. When you multiply those things together, you get 160. Is 160 greater than 10? Of course it is. That's why this thing looks so good. It is a normally distributed curve. Consider the binomial probability experiment with 10 trials here. When we only have 10 trials, it looks like this one's going to be skewed to the right. So again, find the variance of this binomial probability. That's the difference between this and section 8.1. These are the binomial probability distributions. So still have 1,000 trials. I'm sorry. We have 10 trials only. 0.2 is the probability of the success, so 0.8 would be the probability of failure. And when you take those times each other, you get 1.6. Is 1.6 greater than 10? No. Okay, in fact, it's far away from it. That's why this thing looks skewed right, big time. So this thing's not normal. We cannot assume normality. Wow. The final one. So when the number of trials shrinks, then our chances of being normal shrink too. If the probability of a success shrinks, this thing looks normal. If the probability of a success shrinks, it's harder to be normal as well. So again, we compare the variance of a binomial distribution, and we want to see if that variance is greater than 10. If the variance is greater than 10, you can assume normality and then use all the formulas that we did in 8.1. Here we go. We have 1,000 trials, back up to 1,000 trials, but the probability shrinks. So the probability of a failure, that's also going to shrink. And we multiply these things together, or that's going to increase. When we multiply these things together, you get 9.9. Is 9.9 greater than 10? Whoop. Ah, close. That's why the picture is close. So we can't assume normality. Okay, that's it for pages 1 and 2.